I will start recording now. Hello, good morning, everybody. Welcome to a new seminar in the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Caballero Garcia, Maria Caballero Garcia, from our institute, from IIA. And she will talk about time domain astronomy with future X-ray satellites. Dr. Maria Caballero Garcia is a researcher at the Spanish National Research Council, CSIC, here at the Astronomical Institute of Andalusia under a Ramón y Cajal program. Previously, she was a researcher at the Astronomical Institute of the Czech Academy of Science in Prague. There, she was the PI of the Czech Grant Agency's project entitled X-rays reverberation mapping in accreting black holes. She has been developing her career through 5 postdocs at the University of Cambridge, University of Crete, Observatorio Astronómico de Brera, and as I mentioned, at Czech Republic. During this time, she has become a specialist in X-ray astronomy, with a special emphasis on the spectroscopic and timing analysis modeling of X-ray data from accreting black holes. Currently, she is extending her work in the study of the physical processes occurring during the final stage of the life of massive stars. She is also serving to the ESA science study team for the THESEUS satellites, previous ESA M5 candidate, and currently under phase 2 study, and chair of its science working group, Time Domain Astronomy. So thank you very much, Maria, for accepting this invitation to giving a talk. And the floor is yours.
Many thanks, René, for this beautiful introduction. So for this invitation to give a talk in the IAA, actually my first. So I will start now. I'm gonna talk about the time domain astronomy with future X-ray satellites. As René said, I'm working in the science study team, previous science study team of the THESEUS proposed mission to ESA during the last M5 call. Currently, as a starting point, these are the current ESA X-ray telescopes. We have XMM-Newton, that is this focusing X-ray satellite mirror telescope, and it is devoted to the study of X-ray emitting sources with a relatively not very large field of view, but it is when it studies a source, it is just focusing on it and studying, taking all the X-ray photons from it, and also the ultraviolet photons detected from by the U-boat telescope on board. There is another telescope that is ESA and NASA collaboration. This one is a collaboration with NASA, and it's called the SWIFT. This one is based on coded mask optics and with 2 X-ray telescopes, one that are the XRT telescopes, the BAT telescope, that is the bigger field of view imager at high energies, and also another telescope, ultraviolet, that is called the U-boat. I apologize, I said U-boat in XMM, but it is the optical monitor in the OM instead. With this big field of view for the BAT, the goal is to detect a large field of view in the sky. So the events that are the gamma ray bars that are occurring at any direction of the sky can be covered easily, because we don't know when they happen and where in the sky. Then there is another ESA mission, that is the integral mission, that is based also on the coded mask optics. It contains the IBIS imager, that is this one here, that is detecting hard X-rays. Also, there are two monitors that are called the GMX, are softer, detect photons from softer energy range, and the SPI, that is detecting the highest energy photons from the X-ray sky. The purpose of this satellite is to detect not only it doesn't have such a field of view like a Swift observatory, because it's not devoted only to the detection of gamma ray bursts, but is more focused to the study of gamma ray transients in the galaxy, in our galaxy. This is the list of all the missions of all the observatories sent to space by ESA. In the whole electromagnetic spectrum. We have here the microwaves, and we go to the right. As we go to the right, we go to higher energies, going to the gamma rays in the right side. So the ones in the middle are the ones that are working right now, whilst the ones in the bottom are the ones that are in the legacy of the archive. The ones in the bottom, in the X-ray domain, as you say, is XMM-Newton and integral. We got these two ones. And in the concepts in development, right now we got all of these in the optical, also these ones in the infrared optical. In X-rays, we got the Xerism, that is for high resolution spectroscopy and is collaboration with Japan. The Einstein telescope, that is a collaboration with China and is devoted to multi-messenger astronomy. And the ATHENA telescope, that is also in concept, well, it is actually has been adopted, is for the study like XMM of certain X-ray emitting sources in the sky. There is also the LISA that will be studying not in the gamma ray, in the electromagnetic domain, but in the gravitational wave domain. That is the messenger, another messenger of the sky, that is the gamma gravitational wave domain. And here is the THESEUS proposed mission to M5 that was finally not adopted in M5, but we are working through proposing it again for the next call, that is the M7 call. Here we got all the missions accepted recently by ESA. In the small missions and fast missions are the cheapest missions that have been accepted by ESA recently. In the fast in the F2 program, in the F2 call. Is the last one, and here in the middle is the missions with more budget. Already accepted these ones that are with a budget around 500 million euros, and in the M5, the last one, Envision was selected, that is a planetary mission to Venus. And these are the ones that the large missions with a budget higher than 500 million euros provided by ESA, that the recent ones are the THESEUS, ATHENA, and LISA. What is the goal of THESEUS? THESEUS is the acronym of the Transient High Energy Sky and Early Universe Surveyor. And the goal is to study all the gamma ray bars down to the period of the reionization of the universe. I mean, in the range higher than 6 until 10. In these explosions, gamma ray bars will allow us to understand their environments and the first structures in the universe. Will allow us also to understand the population 3 stars that are the more massive stars known in the universe. And when they explode, they are the candidates, they give us to the candidates of more massive black holes given in this period of time. And all of these things are very cosmologically very interesting. But also another theme that is a secondary goal of THESEUS is the study of the gravitational wave counterparts in the electromagnetic spectrum. The previous consortium, as proposed in the M5 call, was constituted by all these countries, with these countries leading the consortium: Italy, United Kingdom, France, Denmark, and Switzerland, and Spain going in the following contribution, and then all of these countries. And currently, for the next call, there will be some countries added to the list, if accepted. This is the mission as it was proposed and developed during the ESA M5. If accepted as ESA M7, that already has not been selected for a study, but if it would go through a study and accepted, it will be launched in 2037. So it will be simultaneous to many gravitational, to the third generation of gravitational wave observers on Earth, and also with LISA, Athena, and as I will explain in a while. So during the ESA M5 study, the industries developed two models. This is the model developed by the Airbus, and this is the model developed by Thales Alenia, and they are both very similar. As I will explain here, the telescope is like this. It has got two XGS units that are the units with the biggest field of view. Both of them provide a big field of view, and also the instruments with the highest gamma ray detectors, and also the softer X-ray units that are these ones. They are two units. They also cover a very big field of view that is good for the follow-up of gamma ray transients that are random events in the sky. And there will be on board an IRT telescope that it will be 70 centimeters of diameter. So with a spectrometer also included, in order to determine on board the redshift of the gamma ray bars located from the redshift universe that we are expected to be emitting in the infrared. Here I explain in detail what are the soft X-ray imagers that it's covering the 0.3 to 5 kiloelectron volts. And this is consisted by a set of two lobsterite telescopes with a field of view of 0.5 steroradians, with an pointing accuracy between 1 and 2 minutes. The infrared telescope that is working in this range of the infrared between 0.7 and 1.8 micrometers. It's a 0.7 meter class infrared telescope with a 15 by 15 field of view. And it works in both imaging and spectroscopy capabilities. The X-rays, the XGS, that is the acronym of X gamma rays imaging spectrometers, works in this wide energy range between 2 kiloelectron volts to 20 electron volts, and it's a set of two coded mass cameras with the last technology, monolithic bars of silicon diodes coupled with cesium crystal scintillators. It provides two steroradians as a field of view and a source location accuracy of 10 minutes in the 2 to 150 kiloelectron volts, whilst in the energies higher than 150 kiloelectron volts, it covers higher field of view of 4 steroradians. That is almost the source of the sky. But in this case, we don't only provide imaging, we don't provide the spectroscopy for this energy, for this high energy range. Here we go into detail into one of these modules of the SXI, where you can see this peculiar shape that is not flat, but is curved and is composed by many cells. This is the so-called lobsterite technology, focusing technology that has been already applied in other telescopes by ESA and also by NASA. And the focal plane detector is not a CCD anymore because this technology will be out of date in the future. So we have to move to the CMOS technology. That is the one that is going to be available at that time. This is what is called, why is it called lobster eye technology for these telescopes? Because it is based on the nature. Lobster is the name of this crab that is in this crustacean that the animals that live on the rivers, and you can see that this eye is very. I mean, the animal can look at any direction of the sky, and it has many cells. When we look at very very close into this eye. And this is the artificial structure made by humans trying to resemble this natural structure from the crab. So with this way, we pretend to detect X-rays coming from any direction of the sky as far as possible and with the highest sensitivity possible. This is the typical PSF from an X-ray source detected with the lobster eye technology. Is characteristic because it has 4 wings, as we can see here. And this is technology has been already applied for the Rosita telescope, this German-Russian mission. And with this technology, we have seen from Rosita that we can obtain very beautiful images from the X-ray sky because it has a very high sensitivity and wide field of view. Then we go to the structure of the XGIS monitor. This is one module of this monitor. We see here the coded mask, and this is the tube of the monitor. You can detect thanks to this length and the material inside, you can detect this broad energy range of photons between 2 electron volts to 20 mega electron volts. Here we go into the structure of this monitor, of this module. We see here on a scheme, the X-ray photon comes here, and it passes through this tube. In the surface here, you can detect the softest X-rays or gamma rays, whilst the gamma rays, because they are more powerful, they go deeper into without being detected by the surface, but it gets detected by the scintillator detector, and this is the way to detect the deeper gamma ray photons. And the luckiest ones go into the detector area that are detected and are where you can apply the coded mask technologies that are already used by current Swift and integral satellites in order to detect these elusive but already often detected photons. This is the infrared telescope, and it is based on consisting by an off-axis coarse telescope that it has this structure. The rays in the infrared will be traveling in this way that you can see that is not a typical, I mean it's like a very compressed way to make the photons to travel. They come here.
Maria, sorry. This slide, we cannot see it, the new one, the infrared telescope, for some reason. Oh, now, yes.
Oh, I'm sorry. Okay, so this is the infrared telescope with this coarse structure. You can see that the photons are going in this way, that in order to make in a compact region the detection of these photons by a spectrograph and imager. So what is the goal of the THESEUS satellite? The THESEUS satellite has as a core program the detection of the gamma ray burst as far as in this area between redshift 6 and redshift 10. This is the area that is the period of the reionization of the universe. Maybe we can detect any. It depends on the transparency of the gas when it was during the dark ages, right after the explosion of the Big Bang. So this period is between 400 million years after the Big Bang and 1 billion years after the Big Bang. So with the detection of these gamma ray bars, you can study many properties of the gas surrounding these events, and this will allow us to detect, to derive properties of the matter in this period of the universe, very poorly studied so far, but it will be studied currently and in the near future by the James Webb Telescope. Nevertheless, we expect to discover more events or more interesting physical phenomena using the X-rays instead of the pure infrared. And this is why we claim that THESEUS, for the study of the epoch of reionization, it will be also very important and interesting to use tool. The second goal for the core program is the study of the gravitational waves. You know, as far as that the most explosive events in phenomena in the universe originate, like, for example, the collision of two neutron stars, of two black holes, produce the most energetic phenomena in the universe. And these are called the gamma ray bars, because they emitting gamma rays, but they also emitting in gravitational waves. And here you can see the emission in gravitational waves as it was detected by ground, by the LIGO interferometer. And here you can see the frequency of the was going very, very high of this event, of the turning around between both components of the binary until they collided, until they collapsed. That is the time zero for gravitational waves. And in the electromagnetic emission, we saw that after some period of time, there was a pulse in the gamma rays. And this is what we detected as electromagnetic counterpart from ground with the integral satellite and other satellites from ground. So with THESEUS, we will be able, to detect these events in near real time. We don't need to wait on ground, but it will be detected in near real time. But THESEUS will not be working alone. In spite of its autonomous properties, it will interact with other large observatories that will be available by that time, at the end of the 30s, beginning of the 40s. That will be the 30-meter telescopes on Earth, like the extremely large telescope. Also, well, we don't know exactly if it will be leaving the Rubin Observatory by then, hopefully. And the square kilometer arrays, also the Cherenkov telescope array, the neutrino detectors, and also the third generation of gravitational wave detectors that will be operating by then. THESEUS will be able to provide alerts to all these, and also to ATHENA, I forgot to tell, will be able to provide alerts to all these telescopes and infrastructures in space and on Earth, and it will also be getting alerts from them to observe some interesting targets provided by them. So this is the sense of the double arrow here. As here I show the two possible structures, very possible that we will work in telescopes on ground in the 30s, that will have also 30 meters, with diameter telescopes. So this is the Magellan in the right, and here this is the Magellan, and this is the 30-meter telescopes. And not only this, it will be also measuring, as an ancillary program, will be measuring also any transient in the sky. That is, for example, black holes, novae, thermonuclear bars, any transient phenomena that will be emitting in high energies or that will be interesting to be observed in infrared, in near infrared, will be observed also by this satellite. And these are the sources interested in X-rays to be observed in the auxiliary program that is called also the time domain astronomy program by THESEUS. The time domain because it will be observed in X-rays in the X-ray time domain. This is time, and this is the flux of these sources. The most powerful sources are the magnetars that will be observed with shortest exposure times, and they have the highest fluxes. Afterwards, immediately the thermonuclear bars, and then we will be having the X-ray binaries, the classical novae, the flaring stars, AGNs also, but we need longer exposure times. For all this, for the AGNs, transient disruption events, and ultraluminous X-ray sources. Or you can see a beautiful review of all these cases and how they will be observed with THESEUS in this paper I show here by Mereghetti et al. In 2021, published in Experimental Astronomy. And now I go to the X-ray spectroscopy and timing studies that I have been doing during my career, previously coming to here to the Instituto Astrofísica de Andalucía. And I will be focusing, these are interesting sources to be studied for the X-ray facilities by THESEUS, ATHENA, and all the X-ray facilities that will be in the future. And I will be focusing on accreting collapsed stars, or what is the same, X-ray emitting black holes. Black holes are interesting. As you know, the Physics Nobel Prize awarded in 2020, it was awarded because of the discovery of black holes and the determination of the properties of the stars in the galactic center of our Milky Way that are possible only due to the existence of a big mass black hole in the center of our galaxy. So these were the people awarded by this Nobel Prize. Penrose by the contribution, theoretical contribution, and Andrea Goetz and Genzel because of the observational contribution. As you have probably known, black holes are characterized theoretically by their charge, their mass, and their spin. If we suppose that the charge is zero and we don't care about this theorem, the no hair, we consider that the black holes don't have no hair, they are bald. So they can be characterized only by mass and the spin. So how can we weight X-ray black holes? How can we calculate the mass of black holes? So one of the ways is through X-ray spectroscopy from the standard, from the standard accretion disk theory applicable to sub-Eddington flows. We have seen that from the X-ray spectrum, we can measure the temperature, the mass of the black hole through the measurement of the maximum temperature of the black body emission coming from these disks. So from this peak here, this gives the temperature of the innermost part of the accretion disk that is emitting in X-rays. And this temperature is related to the mass of the black hole through this power. So the more massive black holes will be given colder accretion disks, black body components. Also, the X-rays from accreting black holes is rather noisy. So we need some devices trying to deconvolve this noise and produce it into understandable signal, like passing some noise into a passband coder. Here I represent it like a radio, an analogical radio. So here, this is the typical light curve from a black hole. You can see that it is rather chaotic, but in any way, you can see some kind of periodicity that is not real periodicity, but is quasi-periodicity. If we pass this through to the power domain, so you can see that it translates into frequency, into some kind of noise at low frequencies. That is, this kind of noise is white red noise because it appears at low frequencies, and then at higher frequencies we detect an absolutely random noise that it is the white noise, the coil noise, the so-called white noise. Why the study of this noise is characteristic? Because it is related to characteristic time scales of the system, so we can understand the physics of the system. We can infer binary properties, and they are also extremely precise. You know about these periods from the pulsars that can tell us about the period of the binary pulsars, and it gave the Nobel Prize of the pulsars to the Catherine. Well, we know this story of Catherine Barner, that she got the Nobel Prize, not she, but her advisor. Well, we can determine the orbital periods of these binaries. We can determine the size of the emission regions and occulting objects, and also the orbital evolution. This is for the people who study binary orbits in general. But in my case, I'm focusing to the accretion phenomena occurring in black holes. So the study of the fast variability, and we do it through the study of the broadband variability, through the study of the quasi-periodic oscillations. In the case of neutron stars, it is through the study of the bars and superbars, but I will not mention them in here, and through the energy-dependent delays or so-called phase lags in the literature. So what can timing in black holes tell us about? If the matter is extending, the matter that emits in X-rays is extending down the event or until the event horizon of the black hole. And the size of this event horizon is proportional, the radius is proportional to the mass of the black hole. So the bigger the black hole in mass, the bigger this radius is, and also the colder the emission is. But if and the colder the spectrum will be. But if the matter extends to this final orbit, this will be the fastest orbit of the accretion disk. And sometimes we can detect some high frequency QPOs that are coming from, that can be interpreted as the last stable orbit from this accreting black hole that is usually not so stable and is giving rise to some quasi-periodic oscillations in the X-ray emission, as we can see here. This is the X-ray emission, this is the frequency, and this is the power. We see that we don't see a strictly periodic signal. We see that should be seen in if the signal would be exactly periodic, but we see that it is quasi-periodic, so it is a bit broadened. And it is at relatively high frequency, as expected from the innermost stable orbit of a stellar mass black hole that is a few hundred hertz. So this is commensurable to the last stable orbit of an accreting black hole. These quasi-periodic oscillations were interpreted as coming from the last stable orbit around this black hole binary, that is XT J1550 minus 564. There are also another kind of quasi-periodic oscillations, but they are low-frequency quasi-periodic oscillations. They don't appear at hundreds of hertz. They appear rather at 10 hertz or even less. And they are not related to the innermost regions of the accretion disk. They are related more to the farther regions from the black hole. We don't know yet from what part of the or what phenomena are they coming from, are giving rise to these features. But they can be classified as 3 types of features: type A features that are in this kind of noise, and these peaks, this kind of peaks, and they are relatively low signal. Then the type B features that are slightly more coherent, and they appear with other features as well, quasi-periodic, and with relatively weak power at low frequencies. And then the most known and the ones that can give us more information that are the type C features, that you have a more prominent QPO typically, with some others as well, and a more powerful low frequency noise here. So these features are usually associated to the accretion rate or accretion state of the black hole, rather than the innermost stable orbit of the black hole. What is the accretion state of the black hole? Let me check the time. Okay. The accretion state of the black hole. So we have the black holes as the accretion rate increases, as we see here in the diagram. They pass through different states. The first one is the quiescence. The quiescent state, then it goes to the hard state, that it is this one. Then it passes through the intermediate state, and it finishes in the thermal state, thermal dominant state. This is in the if we consider the optically thin and geometrically thick corona, and we interpret that the corona is ADAF, as it can be seen in this paper, famous paper by Esin. We have the accretion disk, as the accretion rate increases, is extending down and closer to the black hole. And the innermost part of the accretion disk is filled by this corona that is in principle very thin, optically thin, but it increases in optical depth as the accretion rate increases. We also have this jet that is coming from the innermost parts, and is the black hole expelling matter outside, that is also increasing its density as the accretion rate increases. And at some point during the thermal state, this corona that has been very dense during the intermediate state, and also the jet, disappear. They both disappear. It's like the corona gets cold enough that the electrons just condensate, and all the matter is expelled through the jet. And then we end with this thermal state that has no corona, but has an accretion disk that is extending down to the innermost stable orbit of this black hole. This is the spectral evolution of this emission of a typical black hole, GX339-4. We see it here, the typical spectrum of a black hole during the low hard state, and a bit enter into the hard intermediate state. This is the evolution to the soft intermediate state that is getting more emission from the thermal component, from the innermost part of the accretion disk. And this is when it gets softer and softer, and this is when it gets to the high soft or thermal dominant state, when we see that the corona is emitting very low in the high energies, and we got a prominent emission from the innermost part, thermal innermost part of the accretion disk. This is the typical Q diagram of an accreting black hole in the standard accretion disk theory, as GX39-4 is following typically. So the Q diagram, this is the hardness and this is the intensity. We call it Q diagram because the accretion in black holes start in this point during the low state, and then the accretion, the intensity increases. The low hard state develops like this. The intensity increases without any deviation of the almost any deviation of the hardness that is the hardest that can have a black hole. And during this period, there is only compact emission by a jet observed in radio and infrared. And in this point, when the intensity is the highest, then the black hole goes through this line that is going down through the hard intermediate state down to the soft intermediate state. It is getting softer, but the intensity doesn't change much. But we see that during the soft intermediate state, there has been an episode of the blob emitting corona in radio and also in the infrared. So we see that the spectra starts to change in hardness madly. Also, the intensity changes a bit. Here is where we see the type C QPOs. And then it goes to the thermal dominated states when the QPOs disappear. The radio emission and infrared emission disappear as well, and we only have the X-ray emission from a thermal disk. Then, when the intensity of the disk gets low enough, then and the accretion rate is supposed to be low enough, then it goes back to the point of starting point through a hysterical process, because it doesn't go at the same process as it was coming in. It goes back with a different intensity, but it goes back in a similar way, but with much lower intensity down to the quiescent state. So these are the properties in detail that I have been telling to you, but I will not tell you in words, because I have explained it to you more or less in the previous slides graphically. But this picture, the Q diagram, and this standard disk theory picture, sometimes is not working. And this is, for example, it's not working for this microquasar in our galaxy, binary called GRS 1915+10. This is a source that during most of the time, during decades actually, it's accreting at near the Eddington rate. So it is also experiencing some state evolution that is not the Q-shaped diagram that I showed you before, but rather the inner disk radius decreases when the accretion rate is decreasing, also when the luminosity is decreasing, and it is as opposite of what we expect in the standard theory. So it's like when the innermost part of the accretion disk is closer to the black hole, we don't have jet emission, and we don't have the emission typical we don't have the highest intensity, and this was difficult to interpret in the framework of the standard accretion disk theory. So we have to move to another kind of accretion theory. And at the end, after several years of discussions, the people have arrived to the consensus that we have to move to the thick accretion disk theory or the slim disk theory. The accretion disk is not as optically thick and geometrically thin as we were supposing, but is rather the opposite, is optically thick and geometrically thick and optically thin, as I will explain later. So instead of a Q-shaped diagram, as we can see here for a highly accreting source, that it is this one, NGC 5408X-1, the source gets stuck into a small range of the Q-shaped diagram, and it moves in this during this whole period of accretion, and it gets stuck in this small area. For these sources that are the so-called highly accreting sources with a different emitting process that we suppose, but we don't know yet what is this slim disk accretion regime is. if we analyze in the standard accretion rate theory, we apply the same borders that we know in the standard accretion rate theory. The X-ray spectrum can be decomposed by the power law in the high energies and a soft black body component with a very cold temperature of between 0.1 and 0.5 kiloelectron volts, that it is translated to a is cold, so it can be translated to very high mass black hole being with 10 to the 3 to 10 to the 4 solar masses. But this has been seen 3 years that this is not possible. These black holes don't exist. We don't know of them through the X-ray spectroscopy so far. And we also, when we try to represent the black hole binaries during in this diagram, temperature luminosity diagram, we take all the black holes known in the galaxy that many of them follow the expected standard accretion disk theory that are that is the line here, but the ones that don't follow the standard accretion disk theory and are supposed to be highly accreting sources are these ones in the circle. That are the highly accreting sources. They are all stuck in spite of spanning large amount of luminosities in a low frequency, in a low temperature and range that is between 0.1, 0.5 kiloelectron volts, this temperature, cold temperatures. So this implies that we are if the standard accretion disk theory would be right, that they all will have between 10 to the 3, 10 to the 4 solar masses, but we know that it is not true. So the theory we are interpreting these ones is not correct, and we have to move to another theory. With this another theory, and if we understand that these ones are accreting at super Eddington level, not the standard regime, but in the super Eddington level, and then we infer masses of maximum 30 solar masses for the black hole. Or even in some cases, we are inferring neutron stars for this compact object. So what happens to the accretion disk when the accretion rate is increasing? When the accretion rate is increasing, the vertical scale of this accretion rate is increasing until some point that this accretion, this disk is very, very wide, and it is optically thick. Optically thin and geometrically thick. It's like its path, and it's like a donut, and it was actually called by now called like a polished donut by some researchers, polished donuts or slim discs. And this is the representation of one of these discs, like a polished donut. This is the typical shape of a polished donut without the hole in the middle that are the normal donuts. So what happens with the masses of the black holes between 30 and 100 solar masses? So in this case, we have to move to another, away from the electromagnetic regime. We have to go through to the gravitational waves because they have given important clues into this aspect. We have to thank to this 17th Nobel Prize of the discovery of the gravitational waves to these 3 people here, Weiss, Barish, and Thorne, that are not astronomers but are theorists, and they discovered the gravitational waves. So if this is the range or the ranges of solar mass of the black holes known as a function of the solar or their mass represented in solar masses, we see that all the black holes with masses infrared in X-rays have a mass lower than 20 solar masses, whilst all the black holes with masses higher than 20 until 70 more or less, or 100, have been detected not the electromagnetic counterpart because they don't emit in electromagnetic counterparts. We don't know why exactly why this happens. We have to discover it in the following years, thanks to the interconnection between gravitational waves and electromagnetic facilities like THESEUS, for example, or ATHENA, or any other satellite observing also in the electromagnetic counterparts. They have been detected in gravitational waves to have these masses. So what is the current statistics and forecasts of the X-ray emitting black holes? So far, we have detected 66 black hole transients, and they have been catalogued. And we have detected 132 outbursts detected during the period in between 96 and 2015. They typically have 7 outbursts or 8 have been detected per year, as from Swift and Integral, and it is expected to detect a mean value of 2 new objects per year with THESEUS, and with this rate more or less, but because it will have a wider field of view, then we will detect even more. Majority of black hole transients emit during more than 100 days, so we expect to have high developments in the field, in this field of X-rays time domain in black holes in the following years. I want to take here a note about the iron K lines observed with X-rays in AGNs. This is a hot topic for ATHENA, future ATHENA, and probably we will detect something with THESEUS, or if not with THESEUS, through the synergy ATHENA-THESEUS. It is important to detect with ATHENA the iron K lines, because they give us information about the spin of the black holes. And this is a fundamental property, as I told you before in the beginning, of black holes. This is the X-ray spectrum obtained with XMM-Newton during one of the longest, by the combination of one of the longest campaigns obtained with XMM-Newton of the AGN 1H0707. It was published in Nature in the 2009 by Fabian and co-authors, including myself. And we discovered that there was not only the iron K line, but there was even more powerful iron line in the L band. Because this is a very intense feature, we understood that we could understand the reflection from the innermost parts of the accretion disks through the study of this iron L instead of this iron K line that is typically very weak. This brought us to a new era of understanding X-rays, and brought us to the study of the lags versus frequency that is here, the reverberation lags in X-rays. Before this, there were no studies of reverberation in X-rays. So if we study the emission from this line with respect to the power law emission line, we see that there is a delay of a few seconds. And this delay can be understood as the delay of the photons coming from the corona and being reflected to the accretion disk, innermost parts accretion disk, that is emitting also to the observer, but with a lag, with a time lag. And this is called also the X-ray reverberation time lag. Here we have a model that through the understanding of these lags, we cannot infer only the spin of the black hole, but we can also infer the height of this corona that is also understood as the base of the jet, the X-ray emitting jet, and probably the jet in radio as well. But these things is not confirmed so far. We still need to study these synergies, X-rays, radio, infrared, so blah, blah, blah. So through some years, I have been studying this reverberation from some AGNs. There are also some people as well that have been studying this reverberation as well. These co-authors, Wilkins, Taylor and Reynolds, Heineken and Young, they propose different scenarios, but the one most compatible with the data is the corona that is not very extended horizontally, but is like a spherical blow that is moving along the jet of this spinning black hole upwards. So this corona that is moving upwards would give rise to the phenomenology observed for the longest observed AGN so far, at least as far as we understand. So what can we with THESEUS will not be able to understand to do this time lag analysis for AGN because it's not sensitive enough, as I told you. It will be more done for with ATHENA, that will have the sensitivity enough, good enough for that, thanks to its great sensitivity. But we can do some study of X-ray flares coming from nearby, for example, normal stars. This is a normal star, and this is the typical flare from a normal star, we can, the flare is emitting in high gamma rays or hard X-rays, and the flare where it is connecting to the star is emitting in X-rays. This region of the star is emitting in X-rays through fluorescence, and also in optical in these areas what is called with the delay of Neupert effect. If we study these delays, we can study we can infer the geometry of these protuberance flares as well. This is something that already can be done with the sun and with some red dwarf stars during their big flares. And this is, for example, this is the radio spectrum from one of these flaring stars. We can see that there is an iron care line here. And when it's simulated with THESEUS, we can see this beautiful more powerful line with THESEUS than it is with SWIFT. And with this is the light course that we'll be detecting with in optical, and with THESEUS, very intense also light course, more intense than it has been detected so far with XGS as simulated, with a delay that is can be interpreted in the Neupert sphere scenario, but you can see more clues in this paper by Mereghetti et al. 2021. And this is my conclusions. Regarding black holes with THESEUS, black hole transients show spectral states characterized by different spectral shapes and timing properties during their outbursts. They explain in terms of changes in the geometry of the accretion flow around the central object, disentangling the main components that contribute to the overall X-ray energy budget, and follow a spectral evolution of accretion flow will be carried out by THESEUS thanks to its wide field of view combined with its broad band energy coverage. Simultaneous observations will be triggered with high energy spectral resolution telescopes like ATHENA as well, and radio and gamma rays, thanks gamma ray sensitivity telescopes as SK and CTA, which will be complementary to THESEUS for a comprehensive accretion ejection study of these sources. THESEUS offers the unique capacity to perform strictly simultaneous X-ray and near-infrared observations during outbursts. Infrared fluxes are known to trace the X-ray emission, are thought to be an indicator of the strength of jet activity in black hole transients, and that simultaneous observation of these bands will lead to advances in our understanding of jet disk coupling in black hole transients, and also an opportunity for investigating sources in a highly accreting regime close and not above the Eddington limit. So this is the end of my talk, and thanks for your attention.
Thank you very much, Maria, for this wonderful view of the THESEUS missions and the using in black holes. Yes. And as usual, the talk is open for questions. Please raise your hand and do the questions. I have one, Maria, if I can use this for breaking the ice. My field of view is not black holes, but nor X-rays, but it's transient astronomy, observing occultations by solar system objects. And this mission has a very nice telescope in the near infrared that we can use it. So the mission is open for research investigations in other fields that there are not X-rays or black holes?
Yes, exactly. We are now working on the deeper on the synergies working group package that I don't belong, I'm not head, but I know about it. We are proposing to use also the infrared telescope to because it will be during the survey mode, it will be operating, maybe not observing targets of interest, but I mean in the field of view of these targets. Sometimes there will be sources that are not interested in X-rays, but because they are interested in other fields like exoplanets community. We got Andrew Blaine as a chair of this group, and he is very active in the infrared other topics that is not particularly time domain astronomy. And also, I guess, also objects from the solar system as well we are.
Yeah. Can you show again the slide? That slide was with some problems, so I want to see the resolution of the spectrograph.
Sorry for going behind.
That one. No, yeah.
This.
Yeah. Resolution 20. Nice. Wow, this is exactly what we want. Very low resolution. Yeah.
Yes, it's not very, I mean.
Yeah, it's exactly what we need. Yeah. Okay, so I will write to you. Okay, we have another question here, Pepa. Go on, please.
Hello, good morning. Congratulations, Maria.
Thank you.
I enjoy very much your talk. It has been very nice and very helpful to know about this THESEUS satellite. I have two questions. The first one is why they rejected THESEUS satellite in ESA. Envision was the supported mission. Because I mean, now we are entering into the time domain astrophysics from many point of view, from black hole for the people like me that study supermassive black hole, I don't know, the people who study planet or everything. So that is strange to me. Which are the real plan for the THESEUS satellites when it will be ready?
Okay, so the reasons that ESA gave to us is that the mission was, I mean, at the end of the game, there were two competing missions only, that were THESEUS and Envision. Mm-hmm. And ESA has given the reasons that the THESEUS was slightly too expensive for being only ESA contribution. And it was, I mean, Envision is a mission that had NASA contribution as well, and was within the same budget. This was probably one of the reasons that, because we were limited only to the European budget, it was slightly too expensive for ESA because they had to cover many items of the satellite. So this was one of the main reasons. And the other one, I don't remember now, but it was not so powerful as the economical reason, I guess.
Yeah, no, because, well, now we are almost in the dark ages of X-ray astronomy, with XMM is getting older. Fortunately, we're lucky, cross finger. And so that is the only, under my knowledge, the instrument that can perform this time domain is analysis in X-rays, SWIFT. And how you make the comparison between SWIFT and what you expect with THESEUS? Can you still do something?
Yes. Yes. SWIFT, well, we can compare, they are in purpose similar in goals, because we want to understand locate the gamma ray burst, but THESEUS goes deeper because it has an infrared telescope that can detect farther away GRBs than SWIFT does. SWIFT has on board only an ultraviolet telescope. We cannot detect redshifts very far away because counterparts very far away because of this limitation of the ultraviolet. But if we have a very powerful infrared telescope on board, we can detect very high redshifts. So we can go detect gamma ray bursts that are occurring at redshifts between 6 and 10, tens of them actually. SWIFT has detected 10 of them during 30 years of operation. We expect to detect tens of them during the three first years of operations with THESEUS. This is the main difference. Another difference is that, well, probably THESEUS will have bigger field of view than SWIFT. Definitely will have bigger field of view, but it's not the main power because Fermi is working currently, and it also has a very big field of view, but it has not an infrared telescope on board. So the main power of THESEUS is this also together with these X-ray telescopes with a very big field of view, the infrared telescope. This is the main power and difference between between existing and immediate future telescopes that will be operating, like the Einstein telescope that will be operating also, but it has not infrared telescope. So this is basic.
Okay, thank you, Maria.
Thanks to you
for this nice talk.
More questions to Maria? So I was curious also to see how the pointing of the telescope would be, because they need to react very fast from one burst to the other, or maybe to any other point.
Yes.
So how it works?
Yes, in this case, NASA is the winner because SWIFT, if it is called SWIFT, is because it is very swift and rapid to repoint. I mean, like SWIFT is the best. I mean, SWIFT actually the idea was developed for military reasons. And I don't want to say that ours will not be as fast as SWIFT moving, but probably will not. As fast as SWIFT, but this will be compensated by the big field of view of the telescopes that we will be having on board. So we don't need to move as swift because it will be compensated by the big field of view.
Okay. Very good. Okay, last opportunity to ask any question to Maria. Okay, seeing none, thank you, Maria, again for this nice talk.
Thanks to you.
And see you all next week, that we have again 2 seminars on Tuesday and Thursday. Thank you very much.
Okay, bye.